Hello and welcome to the first of our recitation videos for week number 3. In this recitation video, we will be discussing simplicial complexes, going through some examples, and some specific types of simplicial complexes. So before we go ahead and get started, just a comment about this course moving forwards. For the first couple of weeks, the recitation videos were largely independent from the lecture videos. They were review type content, making sure everyone has the necessary background before we really get into topics more closely tied and specific to topological data analysis. But now, as we move closer to the TDA realm, the recitation videos will be pretty closely linked most of the time with the lecture videos. So in particular, with regards to watch order, what that means is this week and for future weeks, unless otherwise specified, it's probably a good idea to watch the lecture videos before the recitation videos, because the recitation videos will, in general, assume that you've watched the lecture videos already and are comfortable with the terms and definitions from the lecture videos. We'll just use those in recitation without necessarily redefining terms or restating theorems, etc., etc. So if you haven't watched the lecture videos for this week, I encourage you to go back and do that now. But if you have, then let's go ahead and get started. So first, you discussed in the lecture videos what a simplicial complex is. In practice, and by in practice, what I mean is in applied practice. So when we're thinking about things from an algorithmic or computer science type standpoint, we're mostly working with abstract simplicial complexes. Recall, abstract simplicial complexes are just sets of simplices where a simplex, an abstract simplex, is simply a set of vertices. So this is how a computer thinks about a simplicial complex. You know, a computer is not going to just picture some simplex in the plane. It's going to say, this simplex, it's a collection of vertices. So what do we need to do to check and determine if a collection of simplices is actually a simplicial complex? Well, a key fact is that in a simplicial complex, all faces of every simplex must also be in the complex. This is really the main barrier that can arise for a collection of simplices not being a simplicial complex. So let's consider the following example. So K, written out in the form of an abstract simplicial complex right here, has 5 zero simplices, 0, 1, 2, 3, and 4. It has 5 1 simplices, 0, 1, 1, 2, 2, 3, 3, 4, and 4, 0, and 1, 2 simplex, 0, 1, 4. A geometric realization of this abstract set of simplices is visualized on the left here with the 5 zero simplices labeled. So look this over for just a moment and think, is this K actually a simplicial complex? So if you've thought about this for a moment, you'll realize that this K is not a simplicial complex. And what is the issue here? Well, we have a 2 simplex, 0, 1, 4, represented by the shaded triangle, which is missing an edge. For this to be a simplicial complex, we would need the edge, or in other words, the 1 simplex, 1, 4. So that's one way that this set could be modified to form a simplicial complex. Another way is we could just delete the 2 simplex. So in particular, this K is not a simplicial complex, but if we let K1 be K union, it's missing necessary 1 simplex, so K union 1, 4. Then K1 is a simplicial complex, or similarly, we could let K2 be K and then remove the 2 simplex, 0, 1, 4. And now either of these are in fact a simplicial complex. So K1 is what we have visualized on the left-hand side currently, and K2 is what we get if we remove all of this aside from that diagonal, which shouldn't have been deleted. So this is a visualization of K2. You can, think for yourselves for a moment and hopefully, justify to yourselves that both K1 and K2 now are simplicial complexes. So this was just a couple straightforward examples. Now let's move on to a few important types of simplicial complexes which are used commonly in practice. So the first that we'll discuss is the Viator-Schrips complex. So this was discussed in lecture, so I won't spend too much time redefining it, though I will actually just state the definition again because it is very, very important. So the Viator-Schrips complex on a metric space x comma dx at scale parameter r is, I'll denote it with this VR superscript r. Sometimes the v is cut off, so if it's just r superscript r, this is also going to mean Viator-Schrips complex. It consists of all simplices sigma, which are a collection of points in x, such that the diameter of sigma is less than or equal to r. And recall, the diameter of a simplex sigma is simply the maximum over the distances between any two vertices in the simplex. So what's an example here? This is a very simple metric space. Recall, this is how we would oftentimes look at a metric space in practice via a distance matrix, as we discussed in recitation last week. So this matrix, you can verify pretty easily that it is a distance matrix. Now let's compute the Viator-Schrips complex for a couple of scale parameters. So if we look at the Viator-Schrips complex at scale parameter 0, it will just consist of the 4 zero simplices. So this is something implicit in the definition of a Viator-Schrips complex, is that all vertices will always be present because the diameter of a single set is just 0, because from the metric definition, the distance between a point and itself must be equal to 0. Then, if we go to the Viator-Schrips complex at scale parameter 1, we see there are these edges connected, because the edges corresponding to these ones. So we have three ones, and then the symmetric 3 ones will correspond to 3 edges that got added in when the scale parameter was increased to 1. And then lastly, the remaining edges get added in at scale parameter 2, the remaining edges 1 simplices, and hence at scale parameter 2 we can look and see, well, the maximum diameter of any simplex in this metric space is going to be 2, because all pairwise distances in the metric space are bounded above by 2. So at time 2, all possible simplices will be added, and so the Viator-Schrips complex at scale parameter 2 of x is actually homeomorphic to the 3 simplex along with all of its faces. And you can verify that pretty quickly. I should also say that we're doing some simple examples here just to visualize and get a better understanding of definitions. In the next video, we will be looking at how to actually compute these simplicial complexes and define simplicial complexes in practice in MATLAB. So that we'll go through some more examples and some more in-depth examples in the next video. As an exercise, for K1 and K2, the simplicial complexes from earlier, defined back here, try to define metric spaces, or define a metric space X, and scale parameters R1 and R2, such that the Viator-Strips complex of X at scale parameter R1 equals K1, and the Viator-Strips complex at scale parameter R2 equals K2. So with comments from earlier, since K has 5 zero simplices, you'll know that the metric space X needs to have 5 points in it, and then from there, there's a lot of freedom. I'll tell you this is definitely possible, and there are a vast array, infinite array of correct solutions. But this is good, fairly quick exercise to try to just ensure your understanding of a Viator-Strips complex. So Viator-Strips complexes are one of the most commonly used, if not the most commonly used, simplicial complexes in practice, but they're certainly not the only one either. Another common type of complex is the witness complex. So the witness complex helps with one of the main drawbacks of a Viator-Strips complex, which is that Viator-Strips complexes can quickly become too big. And that's, of course, a little bit subjective, depending on things like the computing hardware you have available. But namely, as you get higher and higher dimensions, the number of simplices in each dimension is growing drastically. And so, if you want to do things in higher dimensions with Viator-Strips complexes, it's not going to be feasible in practice. So one of the key ideas behind a witness complex is that instead of considering every point in our space as a zero simplex, we're only going to choose some subset of points in the space as our potential zero simplices in the simplicial complex. So I'll give the definition. For x dx, a metric space, the witness complex, which is denoted W, with 3 parameters, L, X, and R. So R will be a scale parameter. X is our input point cloud / metric space. And L is a set of zero simplices, or a set of points, a subset of X. And L is called the landmark set. So L is the collection of zero simplices that we're actually going to build our simplicial complex on top of. Now, a k+1 simplex, or excuse me, a k-simplex, consisting of vertices L0 through Lk, is in this complex if there exists a point x in our metric space such that the maximum distance between x and any of the vertices of the simplex is bounded above by our scale parameter plus m sub k of x, where m sub k of x is the distance from x to its k plus first closest landmark. And here, x is called the witness. So the idea here is that x is witnessing this simplex. Maybe it'll be much clearer if we look at the following example. So suppose we have this collection of points is our set x, and the 3 points that are asterisks here are our collection of landmarks. So in practice, we would be building up our simplicial complex only on with 0 simplices from the landmark set. So you can already see the idea that we're throwing a lot of points from our space out in terms of building our simplicial complex. And so there's just going to be drastically fewer simplices in the witness complex, making it much more practically feasible. So here, if we want to look at when would, say, the 2 simplex between all 3 vertices, all 3 0 simplices, when would we know at what scale parameter r would this 2 simplex exist? Well, the idea is that this point here is a point that is close to all 3 of the vertices in said 2 simplex. And so when the scale parameter r, where this 2 simplex exists, will be determined by precisely how close this point is to each of the vertices. And this point is called the witness. So the witness complex, in general, is very good at picking up things about, say, density of the space. If there are a large number of both landmarks and witness points in a certain region of the space, then the simplicial complex is going to be built up very quickly, and many simplices will appear at a low scale parameter in such a region of the space. One thing that I've not talked about is how do we go about choosing this set of landmarks? Because as you can tell, that could be a very important decision. I mean, say we had a number of points here in some metric space. The idea is we want to choose landmarks so that the simplicial complex on the landmarks, built on top of the landmarks, is representative of the simplicial complex built on the entire space. So if we add this collection of points on the right, and we chose as our landmarks these 3 points over here, well, that's not going to probably yield a simplicial complex that's a good representation of our space. Maybe if we wanted a good representation, we would choose, like, you know, these fairly spread out points, or something like this. I'll say there are many approaches to choosing which points you select as your landmark set, but we're not really going to go into that today because that's more actually on the side of data pre-processing, which is something we'll discuss in a few weeks' time. So for now, I guess just the important takeaway is the definition of a witness complex, and then again, we'll see some examples of this later, and we'll discuss on how we actually go about choosing our landmarks in a few weeks. So one of the other most common types of complexes, which is used in practice, is what's called a sublevel set complex. So let's just start with the definition. Let X be a metric space and F some function from the points of the metric space to the reals. Fix a parameter, little r, and we define the sublevel set complex at scale parameter r, k superscript r of x, f, as the set of all simplices such that the maximum of the function value of any vertex in the simplex is bounded above by r. So what's an example? One quick example is the height function. So height function comes into play very frequently in something called Morse theory, which is very closely tied to topological data analysis. It's a little bit beyond the scope of this course, so we may give a very high-level view at some point, but we're not going to get into it today. So what the height function is quite simply, if you have points in the plane, the height function is simply going to input a point and spit out the y-coordinate. So suppose we have this metric space consisting of these 6 points in the plane, and we take our height function to define a sublevel set simplicial complex, and we do so at scale parameter 2, then our simplicial complex would be what's defined here on the right. There are 3 zero simplices because these 3 points all have y coordinate less than or equal to 2, and then every other, all of their cofaces are going to exist in the simplicial complex as well. One key thing that we can note here with a height function or sublevel set complex in general is that in a Viator-Strips complex, all of the zero simplices from the space will always exist. Whereas here, we have 3 points from the space, which don't exist as zero simplices in this simplicial complex. If we were to increase the parameter, say if 4 were up here, then if we took k4 of xf, they would exist as zero simplices in that simplicial complex, but they don't necessarily exist in every simplicial complex, unlike the Viator-Strips complex. So here's an exercise which hints at another very standard definition of a sublevel set filtration, or excuse me, a sublevel set complex. So here, this is just one definition of a sublevel set complex. It's a standard definition, but there are others. Suppose we have a simplicial complex, which is the power set of x. So we have some set of points x, and we just take every possible subset of x as a simplex to build a simplicial complex. Let f be a function from the simplicial complex to the reals. So now we're not just assigning a value to every zero simplex, we're assigning a value to every simplex, and set k superscript r of x comma f to be the collection of all sigma in k, such that f of sigma is less than or equal to r. So now we're not looking at the function value over all the vertices. In a simplex, we're looking at a function value of the simplex itself. Is k to the r of x comma f a simplicial complex for all possible r, f, and metric spaces x? I'll give you a hint. If I'm having to ask the next question, the answer might be fairly obvious. But if not, what can we require about f to make this hold? So I'll say that there's a fairly straightforward condition that we can place on f such that this k superscript r of x comma f as defined is always a simplicial complex, and this is another common way to define a sublevel set complex in practice. So in this video, we've seen a few different types of simplicial complexes, general approaches for generating simplicial complexes, and in the next video, we will look in MATLAB and the software JavaPlex on how we can define a simplicial complex in TDA software. So I'll talk to you then.